Okay. Hello, everyone. My name is Hye-Jin Park, a postdoc at CEA Paris-Saclay. And today I will talk about one of the projects I did for my PhD at Australian National University. And it's about the cold H1 as a tracer of star-forming gas in nearby galaxies. But I will put kinematically on top there because you will know soon. So let's start with the canonical view of star formation from diffuse medium. So in a galaxy, if you look at the one part of the galaxy, then it's mixture of the warm neutral medium, cold neutral medium, molecular gas, and stars. And this has a cycle. So the warm neutral medium cools down and then form the cold neutral medium, and then further cooling and the collapsing and assembly. It makes molecular clouds, and it becomes stars in the inside the molecular clouds. So and then absolutely there is stellar feedback. And the last part, the molecular gas clouds from the stars, we can see as in the Koenig-Schmidt law shown in the left, the gas surface density and the star formation rate surface density, the relation between them at like high gas density is well correlated. Yes. So, but this, so the star-forming gas tracer has been used, the CO has been used for star-forming gas in galaxies. It works well for the solar metallicity because the CO and the H2 molecular hydrogen are well mixed in the cloud, and we can use the CO as a good tracer. However, if we look at the low metallicity system, the picture changes. So the UV high energy UV photons can penetrate more deeply into the clouds and dissociate CO molecule and leaves the CO dark gas, where the CO does not exist, still the molecular hydrogen still there. And it's been also seen in observation. So double LM is one of the nearby dwarf galaxies, and the C2 line, which traces the medium, the cloud, I would say. And then the CO detection is done, but they're very, very tiny. And then we can see the CO dark regions exist in this galaxy. Then this brings us a question of how do we trace star-forming gas in low metallicity dwarf galaxies? And then we look at the CNM specifically, rather than molecular clouds because the C2 molecular hydrogen is subject to the like high energy UV photons. And they're easily destroyed in low metallicity systems because of the lack of dust, and also their abundance is very low itself. So, and there have been some studies that the star-forming gas can be remained in atomic phase. For example, DKL 2000, they found the cold H1 can be remained at like 10 to 40 Kelvin, which is very low temperature. So we focus on the cold H1 or CNM, and traditionally CNM is traced by the H1 21 centimeter absorption line. And you can see this is one of other very nearby dwarf galaxies called NGC 6822. And even though this galaxy is spread in the sky like 1 degree, but there has been only 2 detection made from the very recent study by LG ABS team. So it's very limited because of because we need background source to detect the absorption line, and also the background source has to be bright enough. So what people do for for detecting the CNM in Milky Way and Magellanic clouds, we do Gaussian decomposition. This is one of the regions in the Milky Way And we do a Gaussian decomposition on this velocity profile and finds the narrow components with velocity dispersion smaller than 2 kilometers per second. Then we define them as a CNM. And then in this paper, Marshall et al. 2019, you can see the this different distribution of CNM and WNM. However, the cold H1 content across a wide range of metallicity and galaxy type remains very unexplored. So this is where the Typhon survey comes in. So this is optical field of view, pseudo field of view survey for 44 nearby galaxies. And it has a very wide field of view covering the almost the optical size of the galaxy. For example, this is a M83 and NGC50-36, which is a very beautiful and big galaxy on the sky. And the Typhon survey has observed 5 nights to cover the whole range of this galaxy. And then you can see each region has like optical spectra, and combining these line ratios, we can find the oxygen abundance or gas phase metallicity. So if you have any questions about this survey, just come and find me. And you can see other few other like field of view surveys. The field of view is pretty much like Typhon survey is like bigger. So and then I've looked for galaxies which has like H1 data cube to do the like test. And from these 3 nearby galaxy surveys, we found the H1 data cube with channel resolution smaller than 4 kilometers per second. And then I have these 7 galaxies from 10% of solar metallicity up to almost solar metallicity here. So this is the total H1 intensity map or moment zero map. And the tool I used is BAYGAUD-PI. So this is a Python-based Gaussian decomposition tool with Bayesian MCMC method. And the advantage of using this tool is we don't need to give them the number of Gaussians. So it automatically finds the optimal number of Gaussians per velocity profile and via the Bayes vectors. And then it just gives us the 2D maps of velocity, dispersion, integrated intensity, number of Gaussian peaks, signal to noise, etc. from the H1 data cube. And then this is the number of Gaussian map of the 7 galaxies, and you can see there are like very diffuse area with the number of Gaussian of 1, but some star-forming regions in dwarf galaxies are found they have 2 or 3 number of Gaussians. And for the spiral galaxies down here, they also have more than 1 Gaussians in the like spiral arms, and we can see the complexity of the velocity profile. So here, we define the colder or narrow H1 or kinematically cold H1 component. So the traditional way to define the cold H1 or CNM is to find the Gaussian component with a velocity dispersion smaller than 2 kilometers per second. However, our collected data is like worse. The channel resolution is not enough good to define the like CNM as Milky Way and Magellanic Cloud like people do. So we define narrow components. And the definition is the colder H1 should follow the bulk motion of the gas disk, and also the narrow component with the velocity dispersion smaller than 6 kilometers per second. And this is just an example of one region of one of our sample galaxies. And you can see the narrow component in green well defined. So this is the map of the total H1 of two dwarf galaxies, narrow H1 and broad H1d rest. And we can find that for the narrow H1 component, they are more likely clumpy than broad components. And we take the fraction, the narrow H1 content over the total H1 content, and make the contour here. So this fourth column is the CO, the molecular gas surface density, and the star formation rate surface density, and the metallicity map from the typhoon data. And what we can find is for some star forming regions, high star forming regions, we can find the narrow fraction is increased. And if you look at the spiral galaxies, narrow H1 components are mostly distributed outside of the galaxy, outer outskirts of the galaxy. And unfortunately, because of the molecular, CO detection has been done in the very inner region of the galaxy, it's really hard to find the morphological comparison between the narrow component and the molecular hydrogen. So we did sort of a radial analysis. So for example, this is Sextanzae, one of the dwarf galaxies we have, and we being the distribution of narrow component fraction and the star formation rate, also the metallicity. And then we this plot is a bit complicated. So each color means each galaxy, and the darker points are the outer side of the galaxy, and the brighter is inner. And then we couldn't find any trend for the dwarf galaxies here, but for the spiral galaxy, if we zoom in, here we can see a higher narrow fraction for the outer region of the galaxy, and also the low metallicity region. Yes, like this. And then we looked at the global trend of these properties. For example, so we take the median of the narrow fraction map and put it in T-type, which tells you spiral or dwarf, and then metallicity and the star formation rate. And we can see the more dwarf the galaxy is, then the narrow fraction is higher, or the lower metallicity and lower star formation rate. However, this is not a good conclusion, I would say, because there is a systematic issue here. So, so here I plot also the physical resolution of the H1 data cube and the noise per channel, so sensitivity, and the inclination of the galaxy. And same for the y-axis, the median of the F narrow fraction. And what we can find is the better the physical resolution has the better higher narrow fraction. And we didn't see any trend for the sensitivity, but also we can find some trend in inclination. So the conclusion of this project is actually we need better data. So there is resolution effect. We have tested by degrading the resolution of one data cube into a coarser resolution, and then see if there is a trend of narrow fraction and the resolution. There is a correlation, a mild correlation, but we can still probably say that dwarf galaxies have more narrow fraction or cold H1, but yes, we are very limited by the sample and the data itself. So path forward for this sort of study will be to have good data from Mongoose survey from Meerkat telescope. They have already scanned 30 nearby galaxies and has a very good channel resolution than the data set we have. And LGLBS, which used all configurations of VLA for 6 nearby galaxies. And this has a very good channel resolution. So it will be a good data set for this sort of test. And HKA, the beam size hopefully smaller than 0.5 arcsecond, and with the channel resolution can be like smaller than 0.1 kilometer second, which is well below the CNN velocity dispersion criteria. Yes, so here's the takeaway message. So we started with this project with the question of how do we trace star-forming gas in low metallicity dwarf galaxies. And then we used a Typhon survey to find the better metallicity of the galaxy, and used BAYGAUD-PI to find multiple Gaussian in like velocity profiles. And we found the trend of the higher narrow fraction for the low metallicity systems. However, we still need better data in spatial and spectral axis to trace CNM properly. So here is the QR code to my paper related to this, and I will end here and happy to take questions. Thank you.
Thank you very much. Questions? Yes.
Thank you for the nice talk. I was wondering how you derive the kinetic temperature of H1 and why you define the 500 Kelvin as the cold H1.
If you just assume the thermal broadening only affected the velocity dispersion, then we can get the like temperature range. And could you repeat the second question? Sorry.
Why you define the 500 Kelvin as the cold H1? And because I think the line width is, or the velocity dispersion is dominated by the turbulent or shocks in large scale.
Yes. Yes, you're absolutely right. If you look at one velocity profile, then it's a mixture of turbulence and and also we can include like different clouds in the same line of sight. Yes. So we already know about this, but the temperature we defined is actually we didn't define the temperature of the cloud we found for the colder H1 or the kinematically cold H1, but if you like in the beginning I mentioned that the cold H1 is found in one of the Milky Way survey by Dickey et al. 2000, and they found the 10 to 40 Kelvin of the cold H1. I think this. Sorry. Yes. Here. Yeah, but we cannot actually find the temperature range of the colder H1 we found in this project because it's very complicated. Yes.
Maybe a quick question about the processing part for the Gaussian decomposition. I'm wondering if each voxel is processed independently or there is some kind of, I don't know, joint processing, because I mean, on your map, it seems to be correlated between neighbor pixels.
So for this tool, there's no assumption of any like neighboring pixel should have similar properties, but we actually had tried. So Marshall et al. 2019, they have a similar code which is called ROSA, but they assume the correlation between like neighboring pixels. But we have tried tested for the same data sets, but we actually had some limitation of the tool. So yes, so there should be something more process to be done in the code side.